Okay, so in this video, I'll be sharing my recent work, fair ranking as fair division, which is going to be presented at this year's KDD conference. And this is a joint work with my PhD advisor, Thorsten, at Cornell University. So I'm going to start off by introducing a high-level motivation of fairness in ranking. And also I'm going to introduce the existing, well-established framework of exposure-based fairness. Then I'm going to illustrate some of the remaining issues and unfairness in the exposure-based framework. Then I'm going to go on to talk about our proposed method, the impact-based axiom, and also the fair ranking method. So roughly speaking, I'm going to completely redefine fairness in ranking via some impact-based axioms. And also I'm going to present a simple and efficient method to guarantee our axioms. So to just to set the stage, there are many applications of ranking in online platforms or online marketplaces, from Amazon Book or hotel search and even the academic conference. So this actually is a very interesting application of the ranking. It seems that last year HTML, the ranking of the accepted papers was optimized based on some estimated serendipity score. But anyways, it's kind of typical rankings focus only on maximizing the user satisfaction metric, right? So let's maximize the user satisfaction. But the fair ranking researchers has been recently thinking about it should be also very important to guarantee fairness among items, or like those being lagged, right? So a bit more in detail, the hotel search is actually a very great example of a fairness consideration in ranking. So it still remains very important to satisfy or maximize utility to the users, right? So it's very important to satisfy travelers. They want to find hotels relevant to their query, like their location or their budget very quickly. But the thing is that the ranking also had some impact on the items or hotel side, right? Hotels definitely earn some money from the ranking. So maybe in this particular example, the third hotel may envy the position that is allocated to the first hotel. Right, so if a hotel cannot get any revenue from the ranking, then there's no reason for that kind of items or for that kind of hotels to continue participating in this platform. So it's very important to fairly distribute attention from the users or the revenue among hotels, as well as maximizing user satisfaction. So academic conference, this is also a great example of fairness considerations. This is very important to satisfy conference attendees as they want to find accepted papers relevant to their expertise, relevant to their interests. This is maybe one of the main purposes of hosting academic conference, of course. But the ranking also had some impact on the item side. Authors of the accepted papers want to get as much attention as possible by presenting their paper at the conference. This is also a very important purpose of the academic conference. Anyway, the high-level motivation of fair ranking is that, typically the ranking system, ranking papers maximize only the user utility by maybe simply ordering items by some estimated relevance scores. But the fair ranking researchers has actually realized that that kind of simple implementation often produces very unfair ranking with respect to how the exposure is allocated to the item side. So for example, the top hotel and the bottom hotel may have very similar relevance, but in this particular example, the exposure is allocated to these hotels very differently, right? So it seems very unfair. So the important question is, so how should we define fairness? And also how should we ensure fairness in ranking to avoid this kind of situation and hopefully to fairly distribute some impact or some revenue among items. And this kind of question is very critical in many applications, including YouTube, Amazon, Spotify, and many others. So let's talk about how to ensure and how to guarantee fairness in ranking in this video. So there's some important notation, items and users in the platform. So here is the relevance function between users and the item. So this is assumed to be known. So there are many papers talking about how to estimate relevance from the data, maybe from the implicit feedback data. But this is of course very important, but let's focus on how to compute ranking to guarantee fairness in ranking given the ground truth relevance in this research in this video. Right, so the relevance is assumed to be known. And it's also important, the exposure function. It's also important, the exposure probability of each position K. But this exposure function is also assumed to be known, right? It's also important to talk about how to estimate exposure from the data, but this is actually kind of the independent topic. So let's focus on how to compute ranking to ensure fairness, given the ground truth relevance function and also the ground truth exposure function. So maybe the first metric to define is the typical performance metric, the utility to the users, and the ranking x, right? So I'm going to denote the ranking by x. So U of X is a utility to the users, and this is now defined as the total number of clicks or expected number of clicks given by ranking X in the entire platform. Right, so this is easily defined based on the position-based model, the popular model in information retrieval. So the click probability is just a product of the exposure function and the relevance function. And the X, so this is a stochastic ranking. So this is what we want to optimize for some objective. So this is a probability of an item I being presented at the case position in a ranking that is shown to user U. So what I'm doing here is just take the expectation of the position-based model over the stochastic ranking to define the user utility metric, which is the total number of clicks. But this is actually very flexible, right? So this is just one example. So it can be a conversion rate, dwell time, or DCC metric, basically whatever you want. But the important stuff here is the typical ranking papers, typical ranking systems aim at maximizing only the user utility metric. So this kind of argmax, the max ranking has been considered as an ideal ranking under the typical formulation. But we actually have a very different motivation from the fair ranking perspective. So we also want to fairly distribute some impact to the item side as well as maximizing user satisfaction. So I'm going to also define kind of the impact that each ranking X has on each item I. Right, so impact I of X is the total number of clicks given to each item rather than the entire platform under ranking X. So this is actually very similarly defined compared to the user utility metric, but I just dropped the summation over I because this is, the impact is defined for each item. Right, so it's just a expected number of clicks given to each item. And actually, this is very straightforward, but there's a very important relation between the user utility metric and also impact on each item. So the total number of clicks in the entire platform should be equal to the sum of item impact, right? The impact is the clicks for each item. But anyway, the important motivation in fair ranking research is we also want to fairly distribute this kind of impact or clicks or revenue among items, as well as maximizing user satisfaction. Of course, user satisfaction remains very important, but we also have to care about impact. So how should we do this? So there's actually a very established framework, which is exposure fair ranking. It's a very simple, high-level framework for fair ranking literature proposed by 2018 papers, some seminal papers. So this actually saying the very simple stuff, right? Let's maximize the user utility is a typical metric, but under the exposure fairness constraint. So maybe in other words, this is the definition of fairness in ranking, because ranking that satisfy this exposure fair constraint has been considered as a fair ranking in this exposure fair framework. And after satisfying this exposure fair constraint, we still have some chance to maximize the user utility. It's a typical performance metric. So this definition of fairness in ranking is simply speaking saying that let's allocate exposure, right? Amount of exposure proportional to item merit. So let me more precisely define what is merit, what is exposure. So, but actually that's very simply defined, right? So the merit is just the global or average popularity of an item I in the entire platform. And this is defined independent of the ranking X. So this is defined uniquely for each item and defined by just taking the sum of the relevance function over every user in the entire platform. So this is just the popularity of each item I. So in contrast, exposure depends on the ranking X. So given ranking X, exposure is defined as the total exposure allocated to each item I under ranking X. So this is defined by taking the expectation of only the exposure function, but just basically the amount of exposure for each item under given ranking X. So it depends on ranking X. So go back to the high level exposure fair ranking. So this actually is just saying that let's allocate the amount of exposure proportional to item merit. Or maybe in other words, items having similar merit should get similar amount of exposure. And even after satisfying this constraint, we still have some chance to maximize the user utility. So this is the exposure fair ranking. It's very simple, making a lot of sense. May not be the only way to define fairness, but at least one of the reasonable ways to define fairness. And actually, this is very popular. Many recent papers in fair ranking actually rely on this high-level exposure fair framework. Yeah, so then from now, I'm going to use kind of a toy synthetic simple example to see how the exposure-based framework actually works, and also possibly to find some remaining issues or remaining unfairness in the existing exposure-based framework. So here's a toy example of the basic setup. It is actually very simple. There are only 2 users and 2 items. And another simplification I'm going to make here is about the exposure function. So the exposure probability of the first position is now assumed to be 1, but that of the second position is now assumed to be 0. So from the item side, it's meaningless to be presented at the second position because there's no attention from the users at the second position, unfortunately. Okay, so this is a basic setup of the toy ranking program. And we also know the ground truth relevance table, right? So there are some relevance values between users and an item. Larger the more relevant. And given this true relevance table, we can also calculate merit for each item, right? So 0.8 plus 0.5, 1.3, 0.3 plus 0.4, 0.7. So according to the merit, the first item is much more popular than the second item in this market in this example. And then given this relevance table, the question to ask here is, so then for each user, which item should be ranked at the top position in the ranking with what kind of probability? Especially to guarantee item fairness, as well as maximizing user satisfaction. The question itself is pretty simple, but seems to be very difficult to answer, right? Because in this example, in this market, the first item seems to be, well, definitely much popular, much relevant. But it's also true that the second item also had some relevance, right? So given the situation, how do you balance the trade-off between the item fairness and also the user satisfaction, right? So let's think about what's going to be the desirable ranking in this example. So maybe as a warm-up, as a practice, I'm going to start off by implementing kind of the max ranking or the conventional ranking, which maximizes only the user satisfaction and there's no fairness consideration. So to implement this max ranking in the example, let's see the users one by one. So for the first user, 0.8, the relevance of the first item is much larger than 0.3. So we should recommend the first item with 100% at the top position in ranking for the first user. And also for the second user, 0.5 is larger than 0.4. So we should recommend also the first item at the top position in ranking for the second user. Right, so this is the max ranking. Let's allocate all available exposure for the first item, simply because the first item is more relevant, and also there's no fairness considerations at this moment. And given this max ranking, we can also calculate the total amount of exposure for each item, right? So 1 plus 1 is 2. So this is the amount of exposure that is allocated to the first item. And actually, there's no exposure allocated to the second item under the max ranking. And we can also calculate impact for each item given by max ranking, right? So impact is kind of the number of clicks or was the revenue given to each item under some ranking X. So to calculate impact, we should just take the weighted sum between relevance and exposure based on the position-based model. So 0.8 times 1.8, 0.5 times 1.5, sum up to 1.3. There's no exposure for the second item, so there's no impact for the second item as well. And we take the sum of impact to finally get the user satisfaction of the max ranking, which is 1.3. So this 1.3 user satisfaction is actually really large. This is indeed the maximum achievable, maximum possible user satisfaction given the true relevance table, because the max ranking simply maximizes the user satisfaction. And we also know that the ground truth relevance table. But the thing is that maybe from the fair ranking perspective, this max ranking seems to be very unfair, especially for the less popular item, right? Because under the max ranking, we now see that the second item really gets nothing, no exposure, no impact. So definitely there's no reason for the second item to continue participating in this platform. So we should also care about item fairness. So let's then implement the very established framework, the high level framework of exposure fairness. So here is the ranking led by the high level exposure fairness framework for exactly the same toy example, the toy ranking program. So exposure fair ranking suggests that we maximize user satisfaction, the conventional metric, but under the exposure fair framework, let's allocate exposure proportional to merit. And this is exposure fairness. So let's do some stochastic ranking for the second user, right? So for the first user, the exposure fair ranking still suggests to recommend the first item at the top position in the ranking for the first user 100% deterministically. But for the second user, the exposure fair ranking framework suggests kind of a stochastic ranking to recommend the second item 70% at the top position, and the remaining 30% goes to the first item. And the point of doing this stochastic ranking is that, so by doing this stochastic ranking, we now satisfy or guarantee the exposure fairness constraint. right? So 1 plus 0.3 is 1.3, and the remaining 0.7 is allocated to the second item as the total amount of exposure. So we now realize that under this stochastic ranking, the exposure fairness constraint is perfectly satisfied, right? So maybe in other words, this is the perfectly fair ranking suggested by the exposure fairness framework, because we now perfectly satisfy the exposure fairness constraint. So we can also calculate the impact for each item given by this kind of the perfectly fair ranking. So let's take the weighted sum between relevance and exposure again. So 0.8 times 1.8, 0.5 times 0.3.15, sum up to 0.95. And similarly, we're gonna get 0.28, which is the impact or maybe the number of clicks or the revenue given to the second item under the exposure fairness. And we take the sum of impact 0.95 plus 0.28 to finally get 1.23, which is the user satisfaction of the exposure fairness framework in this example. So this is, of course, a little bit lower than the max ranking because we have additional constraint. But the point of this exposure fairness framework is that under this perfectly fair ranking, the second item actually gets some impact, right? 0.28 number of clicks under the perfectly fair ranking. So this is the introduction of the exposure fairness framework and how the exposure fairness framework works in the two example. Okay, so then the question from now is, so what do you think about this perfectly fair ranking? This is actually defined, or this is indeed defined as the perfectly fair ranking in the existing framework because we now satisfy the exposure fairness constraint perfectly, or the exposure is perfectly proportionally allocated to the items according to their merit. So this should be the perfectly fair ranking in the existing framework. And what do you think about this? Do you think that this is really perfectly fair or not? Right? Again, the question itself is pretty simple, but maybe difficult to answer. Of course, compared to the max ranking, the naive ranking, the conventional ranking, this perfectly fair ranking should be at least better than the max ranking from the fair ranking perspective, because the second item now gets some impact, right? 0.28 impact towards the number of clicks under the perfectly fair ranking. So it should be a little bit better, or at least better than the max ranking, but do you think that this is sufficiently fair or not? It seems to be a challenging question, but actually we clearly indicated the unfairness or some issues of this perfectly fair ranking in the existing framework. So the idea to find out some unfairness is actually to compare this perfectly fair ranking with kind of the baseline ranking of kind of the uniform random ranking. So here's a uniform random ranking. This is a very simple ranking of just a uniform random permutations. So let's recommend the first item 50%, and let's also recommend the second item 50% as a top position for every user in the platform. So this should be the baseline ranking, or the weakest ranking we can think of, which is achievable without really doing nothing. Now we don't have to implement any optimization, any machine learning method. We don't have to know any database information when implementing this uniform random ranking. So it should be the baseline, right? The minimum achievable result without really doing nothing, right? So maybe we have to outperform this uniform random ranking in every possible way when we implement some optimization method or machine learning method in implementing some ranking algorithm. So let's also calculate impact distribution under this uniform random ranking. So again, let's take the weighted sum between relevance and exposure, 0.8 times 0.5, 0.4, 0.5 times 0.5, 0.25, sum up to 0.65. Similarly, we're gonna get 0.35, which is the impact given to the second item, even under the uniform random ranking. And finally, by taking the sum of impact, we're gonna get 1, which is the user satisfaction of the uniform random ranking. Of course, way much lower than those of max ranking and also exposure fairness framework, because this is the weakest ranking we can immediately think of or immediately we can implement. But we now also realize that the second item actually guaranteed to get 0.35 number of clicks was the impact, even under the uniform random ranking. So it should be a very interesting phenomenon, right? What I mean by that is, so let's again compare the impact distribution of the uniform random ranking and also that under the perfectly fair ranking, the exposure framework. And we have actually already calculated that the second item actually guaranteed to get only 0.28 under the perfectly fair ranking, the exposure fairness framework. But we now also realize that the second item actually guaranteed to get 0.35, but even under the uniform random ranking, the baseline ranking, the weakest ranking we can think of. Okay, so to summarize the point, actually the first item should be very happy under the perfect fair ranking because he or she gonna get a much larger impact compared to that under the uniform random baseline. But we now realize that the benefit given to the first item is actually totally at the cost of the second item. Right? The second item actually had some loss of impact, even compared to the weakest or was a uniform random ranking as the minimal baseline. So how come we can say that this is the perfect fair ranking? Even though some item becoming the superstar compared to the uniform random ranking as baseline, while some other item becoming clearly the poor compared to the uniform random baseline. The exposure fairness framework seems to produce a large and obvious clear disparate impact between the first item and the second item. And the problem is that this is defined as the perfect fair ranking, or this unfairness is happening even under the perfect satisfaction of the exposure fairness framework. Again, how come we can say this is the perfect fair ranking? Should be very unfair. So that's actually one of the unfairness we indicated in our paper. And actually, there's another one, right? So another unfairness issue is actually more related to the envy between the items. So here is exactly the same table, the impact distribution under the exposure fairness or the perfect fair ranking. So we see some ranking result towards the exposure allocation for each item under the exposure fairness. And to see envy between the item or to quantify envy between the items, let's for now swap the ranking of the two items with each other's ranking as kind of a hypothetical thought experiment. And we immediately realize that by swapping the allocation or swapping the ranking with each other, right, between the two items, only the second item actually increases its impact when we swap the ranking with that of the first item. And this should be the clear indication of the envy from the second item for the first item, right? So to summarize a bit, from the perfect fair ranking, we now swap each other's ranking, very simple, right? Just swapping the ranking allocated to each item. And now realize that the second item actually increases its impact significantly when we swap each other's ranking. So this means that the second item actually prefers the ranking of the first item rather than its own, meaning that the second item clearly envies the first item. And this envy stuff is actually happening even under the perfect satisfaction of the exposure fairness constraint. So exposure fairness constraint or exposure fairness framework completely allows to produce this kind of envy between the item or amongst the items. And again, how come we can say that this is the perfectly fair ranking, even though it's allowed to produce some envy between the items. So this is the second unfairness we indicated in our paper about the exposure fairness framework. So to summarize, we've actually seen that the perfectly fair ranking, the existing framework, clearly produces some envy among items and also fails to guarantee the minimum number of clicks. Guaranteed even under the uniform random baseline, the weakest ranking we can think of be achievable by really doing the step. And these kind of unfairness issues are clearly suggested in our two example, even under the perfect satisfaction of the exposure fairness framework. So this kind of phenomena is actually clearly suggests that we should completely redefine fairness in ranking, because these kind of unfairness issues are happening even under the perfectly fair ranking, or even if we perfectly satisfy the exposure fairness framework with the definition of fairness in the existing framework. We should clearly redefine completely the entire fairness definition. So one of our main contributions in the paper is actually the redefinition of fairness in ranking. So we redefine fairness. So let's forget about exposure fairness from now, and let's focus on our new definition of fairness, which is the impact-based axiom for fair ranking. So there are actually two parts. So first axiom is envy-freeness. We require that the fair ranking policy not to produce any envy in the entire platform, right? So there should not be any item who envy some other items under fair ranking. So we don't allow any this kind of situation under fair ranking policy in our new definition of fair ranking. So it seems very difficult to achieve and guarantee this envy-freeness, but actually there's a surprisingly simple and intuitive and easy to implement kind of method to guarantee this envy-freeness. So let's wait for maybe 10 minutes until the introduction of the new method. But actually there's another one, another axiom, which is the dominance against uniform ranking. We simply require the fair ranking policy to actually provide at least better impact compared to the uniform random ranking. But we've actually already seen that the perfectly fair ranking in the existing framework clearly violates envy-freeness, clearly violates dominance over uniform ranking, seems very unfair. So there's a clear need for new fair ranking algorithm, given our new definition or the redefinition of fairness in ranking. So the remaining algorithm question should be, so then how can we guarantee our new definition of fairness or our impact-based axioms, envy-freeness and dominance against uniform ranking, possibly in a computation efficient way. In particular, it seems difficult to guarantee envy-freeness, but actually there's a surprisingly simple method to automatically guarantee envy-freeness and dominance against uniform random ranking at the same time. So from now, let's talk about this algorithm equation. So in designing a new fair ranking method, we took some inspiration from the fair division problem considered in the classical game theory field. So fair division thinks of kind of a question related to our daily lives. For example, like how should we fairly divide or allocate fruits among family members? So here's again some arbitrary example, some family members, 3 family members here, and also some set of divisible fruits, right? And this is the heterogeneous preference table. For example, like father likes an apple, and mother and the child like orange similarly. And given this situation or like the heterogeneous preference of the family members, the question is how should we divide or allocate fruits, possibly like fairly or like in a peaceful way. So that's the question of the fair division. So what's going to be your objective function to optimize for the fruit allocation problem? So maybe the standard that was the naive approach is to maximize kind of the total family welfare, right? So let's optimize the fruit allocation so that we can maximize kind of the total family welfare or the sum of each family member utility, right? So the utility of an family member can, for example, be defined by the weighted sum between the heterogeneous preference and also the fruit allocation. But anyway, maybe the standard approach is to optimize fruit allocation by maximizing the sum of a utility of each family member. Should be very standard, right? Especially for machine learning people, and seems not so weird at first glance, I think. But actually, the thing is that when we maximize this total family welfare in optimizing the fruit allocation, actually, we're going to get a very kind of abusive or unethical, unallowable allocation of giving nothing to the child, right? So this is the optimal allocation in terms of the total family welfare. And it actually suggests that let's give apple and banana to father, and let's give orange to mother, and let's give nothing to the child. And this is, again, the optimal allocation, given the objective function of the total family welfare. So the sum of utility, which is 1.8, is the maximum possible total family welfare given the heterogeneous preference table. But I say this is, this kind of allocation, this kind of fruit allocation is totally allowable for anyone else. So it seems that the total family welfare seems at the first glance not so weird, but right, looking at this, the result, the fruit allocation led by the total family welfare, it seems we should completely redefine the objective function. That's actually, roughly speaking, the problem that the fair division community has been thinking about. And there actually is a very great idea, the great benchmark solution proposed in the fair division community, which is a Nash Social Welfare. So this actually is a very nice idea, just a simple modification. So Nash Social Welfare suggests that we maximize the product of the agent utility or the family member utilities, rather than the total family welfare, which is the sum of agent utilities. And it actually turned out that it should be a very nice idea, because if we try to maximize this Nash Social Welfare, we can't have any zero utility agent, right? Because actually a single zero utility agent is enough to make this a global objective 0 if the objective is defined by the product of agent utilities, possibly producing a much more equitable allocation when we think of this as Nash Social Welfare. And this intuition is actually true, and maximizing the Nash Social Welfare is known to guarantee envy-freeness and also dominance against uniform allocation in the kind of the fruit allocation problem, or more generally the fair division problem. And if we actually maximize this Nash Social Welfare in the example problem, we're going to get a very reasonable allocation of giving apple and banana to father and give 50% of the orange to mother and remaining 50% goes to the child. And now the Nash social welfare or the product is maximized indeed. And actually, we're gonna get a very reasonable allocation rather than the unethical allocation that we had in the total family welfare objective. So this is a quick introduction of the field division problem and the idea in the field division community. And if we compare the field division and fair ranking at a high level, it's actually straightforward that there's a cross connection between the two fields, right? You know, the field division and fair ranking. So in field division, we first came up with a naive standard kind of function of the total family welfare, just a sum of agent utilities. Seems not so weird at first glance, but it turned out that results in a very abusive, unequal allocation of giving nothing to the child. So we modify the objective based on the Nash social welfare idea in the field division. Let's also, let's instead maximize the product of agent utilities rather than the sum of agent utilities to have an equitable allocation of, for example, fruits. So this is a field division. And of course, from the beginning, we've been talking about the fair ranking problem rather than a fair division problem. And actually, we now realize that the default objective used in ranking, even by the exposure fairness framework, is the user satisfaction, which is equivalently expressed by the sum of item impact, right? So this seems to be very similar to the unethical, unallowable objective of the total family welfare in the fair division problem. So based on this high-level comparison between fair ranking and fair division, we actually very straightforwardly propose the main proposed, the fair ranking method, which is the Nash social welfare ranking, right? So our proposal is actually pretty simple. Let's just maximize the alternative objective of the Nash social welfare, which is the product of the impact on the items, right? The ranking version of the Nash social welfare. There's no additional constraints. We just modify the objective function. And the resulting ranking is the Nash social welfare ranking, which is actually at least approximately guaranteed to dominate the uniform random ranking. And also, maybe much more surprisingly, it's guaranteed to be envy-free in the ranking program, right? So satisfy the impact-based axioms, our new definition of fairness, by just maximizing the ranking version of the Nash social welfare. And what's also nice about this objective is that by taking the logarithm, we actually get the sum of log impact, which is known to be a convex objective, so efficiently solvable. There's no additional computation overhead compared to the existing exposure-based framework. Okay, so then let me wrap up the video by applying the Nash social welfare to the exactly the same example used earlier, and also to the kind of the synthetic environment. So here's just the two example, the same two example. And the exposure-based fairness, we saw that the impact distribution will be 0.95, 0.28. It seems unfair. The one unfairness we indicated in our paper is that when we compare this exposure-based fairness with the uniform random ranking as a baseline, we realize that actually the second item is guaranteed to get 0.35 impact even under the uniform random ranking. But this is actually not guaranteed only for the second item, even under the perfectly fair ranking of the exposure-based fairness framework. But when we apply the Nash social welfare ranking, we're actually going to get a very simple ranking, which suggests that we recommend the first item 100% at the top position in a ranking that is shown to the first user. But for the second user, we actually do also the deterministic ranking, but we recommend the second item deterministically this time. And because this is deterministic, we can very easily calculate impact for each item by taking a weighted sum between relevance and exposure. So 0.8 for the first item and 0.4, which is the impact of the second item under the Nash social welfare ranking, right? And actually, already there's some very interesting, surprising phenomena are happening here. So the first thing is that it's actually obvious that we now succeed in dominating the impact distribution of the uniform random ranking, right? So we now get the impact distribution of 0.8, 0.4 automatically by the Nash social welfare ranking, and it clearly dominates the 0.65, 0.35, which is the minimum guaranteed kind of the impact distribution under the uniform random ranking. So we automatically dominate the uniform random ranking by just applying the Nash social welfare objective. And maybe even more surprisingly, there's no envy in this platform right now. So to see envy, to quantify envy, let's swap the allocation or the ranking between the two items. So 1, 0, 0, 1, which is the allocation or the ranking of the Nash Social Welfare ranking, the original ranking. And when we swap this allocation between the two items, we're gonna get 0, 1, 1, 0. And we see that actually no item increases the impact if we swap the allocation of the items, right, under the Nash Social Welfare ranking, suggesting that there's actually no envy in the original allocation, in the original ranking, which is automatically guaranteed by just applying the Nash Social Welfare objective. So this is just one demonstration under the two example that by simply applying the Nash Social Welfare objective, we can automatically guarantee envy-freeness and also dominance over uniform ranking in terms of the impact distribution. So finally, let me introduce some synthetic results. So there are 100 users, 50 items, and we evaluated the fairness utility trade-off of the Nash Social Welfare ranking and some baseline ranking methods. So utility is just a number of clicks. So let me introduce some interesting fairness metrics. So there are 3 fairness metrics. So one is mean max envy, which is the kind of the amount of envy produced under a given fair ranking method. So basically smaller the better for fair ranking. So better of percentage, which is the proportion of items who improve its impact over 10% compared to that under the uniform random ranking, right? So larger the better for fair ranking. And the worst of percentage, which is the opposite one, the opposite kind of metric, which is the proportion of items who degrade its utility or impact over 10% compared to that under the uniform random ranking, right? So smaller the better for a fair ranking. So here's the result, 3 fairness metrics and the 1 typical metric, which is the user utility. And the x-axis of each figure is the popularity bias, right? So strongest popularity bias mean that there's a fewer number of very popular items in the platform, producing a much more difficult situation to pursue fairness and utility at the same time in the presence of strong popularity bias. And from the result, it's actually obvious that the Nash Social Welfare, our proposed method, is the most equitable, right? The most fair, especially in the presence of popularity bias. So the first result is envy, and we see that max ranking and exposure-based fairness existing method produce a lot of envy, especially in the presence of popularity bias. But Nash Social Welfare, the purple line, is almost always envy-free. So here's the next metric, the better of percentage, and Nash Social Welfare is always 100%, meaning that succeed in providing some positive benefit compared to the uniform random baseline to like the every item in the platform. But this is not true for the exposure-based fairness and also the max ranking. And the opposite metric is worth of percentage. And under Nash Social Welfare, the purple line, no item actually becomes poor under the Nash Social Welfare. So there's no item had some loss in impact compared to the uniform random ranking, but this is not true for the exposure-based fairness and also the max ranking. So based on the exposure-based fairness or the max ranking, actually some items are becoming the superstars, but some other items are becoming the pro. But this is not happening under the Nash Social Welfare ranking. So Nash Social Welfare is the most equitable, while max ranking and exposure-based fairness produce some envy and obvious disparate impact. But we also observed that there's a difficult trade-off between fairness and utility, right? So especially in the presence of a strong popularity bias. So here's a user utility metric, the conventional metric, kind of the user satisfaction remains, still remains important. And under, in terms of this utility metric, Nash Social Welfare is actually kind of the lower utility compared to the exposure-based fairness and the max ranking in the presence of popularity bias. Of course, it's much better than the uniform random baseline, but this is evidence of the fairness and utility trade-off in the presence of popularity bias. Of course, the Nash Social Welfare is the most equitable, but if we try to guarantee attain fairness perfectly in the presence of popularity bias, we have some loss in the user utility. So we actually provided a final contribution, which is the simple extension to the Nash Social Welfare, which we call the alpha Nash Social Welfare. So this is a very simple extension of the Nash Social Welfare by taking the weighted sum of the, the log impact, right? And the weight is the merit. And the merit is just the global popularity, which is also used in the exposure-based fairness. And alpha is a hyperparameter to control the utility fairness trade-off, right? So the larger value of alpha leads to a higher utility, right? So let's prioritize the user satisfaction, while a smaller value of alpha prioritizes a fairness of impact, right? Let's try to satisfy the impact-based axioms, our definition of fairness perfectly. So we can just control the value of alpha to have a steerable trade-off between fairness and utility based on this alpha Nash social welfare. And this is just a simple generalization of the original Nash social welfare, because when we set alpha to 0, is actually identical to the original Nash social welfare. So this actually guarantees a kind of the relaxed or the weighted version of envy-freeness, and also weighted version of dominance over uniform random ranking. And there are some empirical results, the exposure-based fairness, and also some alpha Nash social welfare with different values of alpha. Roughly speaking, we observe that we can choose a variety of fairness utility trade-off by simply tuning alpha, right? So we can have a kind of a very steerable, controllable trade-off by only controlling or tuning the value of alpha based on the alpha Nash social welfare. And also we can choose a very desirable trade-off by correctly tuning the value of alpha. For example, one Nash social welfare achieves the similar user utility compared to the exposure-based fairness, while leading to a much more equitable impact distribution in terms of our impact-based axioms, the orange line. Right, so we can just choose the alpha to maybe pick the one Nash social welfare, or we can also choose the original Nash social welfare to prioritize impact fairness. So to summarize the entire video, the current exposure-based fairness produces envy and also failed to ensure the impact guaranteed even under the uniform random baseline. So these are the unfairness issues we indicated in our paper about the exposure-based fairness through the toy example. So we completely redefine fairness in ranking via envy-freeness and also dominance over uniform ranking to resolve the remaining unfairness of the exposure-based fairness. And by maximizing the product of the impact over the Nash social welfare, just a simple modification in the objective function, we guarantee envy-freeness and dominance over uniform ranking automatically in a computationally efficient way. We also provided a simple extension to the Nash social welfare, which is alpha Nash social welfare, to control the fairness and utility trade-off based on application. So this is the end of the video, and thank you for your interest.